Good day, everyone. Welcome on our webinar. We'll be starting in about 1 minute. In the meantime, please let me know if you can see me and you can hear me by typing in the chat window. Okay, thank you. I see some people are still logging in, so let's give them a minute and we'll be starting. Okay, I guess that's it and we can start. So hello everyone, welcome on our today's webinar. My name is Maciej Antonik and today I'll be talking about 3D LiDARs. Our webinar is scheduled to take about 45 to maybe 60 minutes. I have a presentation. We will have also a short, very simple demonstration of a LiDAR that I have right here. And at the very end, I'll try to answer any questions that might come up during the presentation. Please feel free to enter them in the chat window, and I'll just go through them at the end of the presentation. As you can maybe see, we're not doing this webinar from a nice studio where we usually try to do our webinars from. Unfortunately, I'm just recovering from coronavirus, so I wasn't able to go among other people, and I have to do the webinar from my home office. I hope it's not a problem for you. When I looked at the list of people who registered, I've seen some familiar faces, familiar names maybe rather. So good day to everyone that I already know, and it's nice to see you again. But I have also seen some names that I think I've seen for the first time. So for everyone here, that's the first time where we see each other, or at least you can see me. I wanted to quickly introduce, first of all, Education for Industries, our company. So we are a Polish-based company that specializes in delivering teaching and research solutions, mainly to engineering universities, but also to technical high schools. We're based out of Poland, and we have been on the market under our current name since 2020, but our history goes back to 2013. So back for almost 10 years, well, 9 years right now, we have been on the market working with engineering universities and technical high schools, but also sometimes customers from the industry, working with them on delivering various teaching and research solutions. You can see all of them on our website. Today we're talking about only one of them, which is LiDAR sensors. And me, myself, my name is Maciej Antonik. I'm a CEO and co-founder of Edu for Industry, and I have been operating on the academic market in Poland and Central Eastern Europe for more than 10 years now. If you feel like connecting with me, I think the easiest way is through LinkedIn. So here's a little QR code which you can scan to find my LinkedIn profile. And also at the very end of this presentation, you'll be able to find my email address and also my phone number. You don't have to write it down quickly. Everyone who has registered for this webinar is going to receive an email afterwards with a link to the recording of this webinar, so that you can either see it yourself later or share it with other people that you think that might be interested in this content. This webinar is also supported and coordinated by Ouster. So Ouster is a leading manufacturer of 3D LiDARs. We, Edu for Industry, is their distributor, not only in Poland, but also in other countries of Central Eastern Europe. So if you need any help in choosing, selecting, or just buying those sensors, we're here to help. Ouster has three main models of their sensors. They go from OS0 to OS2. And the difference is the range. I'm sorry, I see I forgot to translate some words here. Zasięg, it's in Polish, that's range. And so it goes from 55 to 240 meters. And the angle of view, the vertical angle of view, goes from 90 degrees for the shortest range to 22.5 degrees in the longest range. And we will talk much more in details about those specs later in this presentation. But before we go to that, I wanted to start with a quick introduction of a LiDAR sensor itself. So for those of you that might not know what a LiDAR is or how it works specifically, here's a quick refresher or introduction to this technology. So LiDAR, it stands for, the word itself comes from English abbreviation of laser imaging detection and ranging. And it's basically a sensor that can measure distance. LiDAR can measure distance in a number of different angles, so in various directions. And it does it by measuring a laser beam that it shoots in one direction and then measures what is going back to the detector. Historically, the simplest LiDARs and still available on the market and very popular are 2D LiDARs. So 2D LiDARs, they can measure distance in various directions, but only on one level. The simplest construction of the 2D LiDAR is a one laser and one detector, so one pair, that's mounted, let's say, in a box like this. And there's a little mirror that can move around, directing the laser beam in various directions. And this way, by taking measurements one by one, as you can see in the example here, where you have the blue box is the LiDAR, there's some room, there's some object, we can measure, take single measurements, get specific points, and in this way get the map of the room and measure the object. 2D LiDARs are still very popular and these days fairly inexpensive, but they have one major problem. The problem with them is that they can only measure existence of an object on a specific height, but they cannot measure the shape of that object. So imagine we have an object that's that has an irregular shape, and here I just did a simple graphic of let's say an egg, but this could be really any shape of an object. If we only have one laser and one detector, so we only can measure one point in a single direction, we just have this one point, and we really don't know what's the shape of that object, whether it's an round object like this one, or maybe it's just a rectangle, or maybe it's something else. In many cases, this information is important because take an example of a mobile robot. Let's say we have a small robot that can go under certain obstacles. Let's say there's a table. If we only get one measurement, we don't know if there's room to go below it or not. So this is why we often need 3D LiDARs. So LiDARs that have more than one laser and detector pair in going into a single direction. This way we can get a number of points in single direction, and this way we can know what's the shape of that object. See, even if I don't get to see the object, I can see by those 3 points that the object is round and it's not a rectangle. And of course, this is just a very simple, very basic graphic to show you how it works. How it works on 3 beams, but in practice, modern LiDARs they have 32, 64, or 128 parallel channels that can look at an object, giving you pretty precise data. And I'll show you some examples later during a demonstration when you'll be able to see how precise this measurement can be. But before we go to the demonstration, let's dive deeper into how LiDAR is constructed. So LiDAR is built really out of 3 main components. You need 3 things if you want to build a LiDAR. First of all, you need a laser source, so something that can shoot lasers. Then you need a detector, so a piece of electronics that can measure the returning laser signal, measure its strength, and measure the time, how long it took it to go there and back again. And also, if you want to have a wider field of view, you need also a scan mechanism. So you need something that can redirect those laser beams into various directions, this way getting the points from various directions and just drawing a 3D map of the whole environment all the way up to 360 degrees. And when preparing those slides, I was trying to think what would be the most important information for you to get out of this webinar. And I tried to put myself in the shoes of a person that has an idea how to use the LiDAR in their project. This could be an autonomous vehicle or maybe a smart city project, and you need to select the best LiDAR for your application. So my first advice is call us. Well, just give us a call, tell us about your project, tell us about your requirements, and we will help you to choose the best LiDAR for your application. However, if you want to start on your own, I'm sure that one of the first things you're going to do is you're going to open the data sheet and try to understand what are the differences between different models and how to read those different parameters that you can find. So on this slide, what you can see is a list of typical parameters of a LiDAR sensor. So this was taken from an actual data sheet of the OS0 LiDAR from Ouster. So this is the shortest range, widest angle LiDAR in their portfolio. And as you can probably see, the data, and this is, by the way, just page 1 of a pretty long data sheet, it's pretty complex because for many projects, one of the basic, most important parameters that you want to look at is range, right? How far can the LiDAR see? Because there are some projects that are indoors, in a small room, or maybe in I don't know, a cave, where you know that the distance is never going to be further than 10 or 15 or 20 meters. And sometimes you're working in a field or on a road where you really want to see objects that are 100 or 200 meters away. So choosing the right LiDAR based on range, of course, is one of the ways to go. But as you can see here, it's not so easy to tell what's the range of a LiDAR sensor. And I'll try to explain you why. So range, it really depends on many number of aspects. Just look here that the range itself, those are, in this data sheet, those are 4 different numbers, 45, 50, 15, and 20 meters. And there are various parameters and, let's say, assumptions taken to measure those distances. So let me walk you through how to read those parameters and why there are so many. So first of all, since we're measuring an object by shooting a laser beam on it and measuring what's being reflected back, the range is going to depend on what type of object do we want to measure. So we would get a different result if we get something that's almost like a mirror or something that reflects a lot of light, and a very different result if we measure something that's black, that's matte, that doesn't reflect a lot of light. So this is why there are 2 different range parameters. One is for 80% Lambertian reflectivity, and the other one is for 10% reflectivity. The difference is that the first one, the object is made of material, like maybe polished metal, that reflects a lot of light. The other one is probably black and doesn't reflect a lot of light. As you can see, the objects that reflect a lot of light, they can be seen from much further away, while the ones that are black and don't reflect a lot of light, the effective range is much shorter. Another thing that influences how far can our LiDAR see are the external light conditions. So as I said before, LiDAR mostly measures the distance based on the laser it shoots itself. However, the ambient light coming from sun or from lamps or from other sources of light, they're also detected by the detector, and they basically introduce noise to our measurement. So here the assumption is that there's 100 kilolux of sunlight, which is basically a pretty bright sunny day. And lastly, after we have defined our ranges, you can see that at the very end, there's something that says there's some percentage of detection probability. Because of how LiDAR works, you're never guaranteed 100% or almost never guaranteed 100% that you can detect specific object. And to show you why, I'll go to the next slide for a moment to show you an example. If you see here on the bottom there's a human. There's a person standing somewhere to be detected by the LiDAR. And here the points that you can see are the single LiDAR points measured in the direction of that person. As you can see, there's quite a few points that hit that person and went back and were detected by LiDAR to detect that there is something there. So the probability that this person would be detected is fairly big. I would say it says 95. It's very close to 100%. So if our project where we're using LiDAR just requires that a person is detected, we can be fairly sure that a person at that distance with this type of LiDAR with this many points will be detected. But if our project requires that we don't only detect person, but we can detect, let's say, the head of that person, or maybe a hand of that person, or maybe to detect whether that person carries something in their hand or not, then the probability that even one of those points will hit the head or something else is much smaller. So the probability of detection, the chances that in this specific frame, one of the LiDAR points really hit, we were lucky enough that it hit that point to detect the head or some more specific smaller part of that person is much smaller. And this is why for each range, for each reflectivity of the object, for each parameters, there are still two options. 90% detection probability. So we know in 45 meters, we are 90% sure we'll detect an object. And 5 meters further, that probability goes down to 50%. So you have to take all of those things into account to really estimate how effective your LiDAR is going to be and which model to choose for your specific application. And from here you can just get basically a good idea, right? If your project, you know, you have very reflective objects, you can be sure that you can work in the 40 or 50 meter range. If your object is not going to be very good for reflecting the light, we're probably looking at much shorter distances. And of course, the best way to check it in the end is, of course, to test the LiDAR. And we at Edu4Industry, we have one LiDAR that we can lend to customers just to verify the measurements, test it on their own, to really check before buying if the LiDAR would fit the needs of that specific project. Next, parameters in the data sheet that you can see here are, well, there's minimum range, because you have to remember that LiDAR doesn't work very close to itself, so it cannot detect objects closer than around 20 something, let's say 30 centimeters. And then there's a number of parameters that talk about accuracy and precision of that LiDAR. The difference is that basically range accuracy, this is a parameter that talks about repeatability of measurements, right? So if you get the LiDAR is in the same place, the object that we measure is in the same place, so we should be getting not more than 3 centimeters from Lambertian, so objects that reflect light well, or not more than 10 centimeters for retroreflectors, so objects that don't reflect light very well. So this is the difference between the actual measurement. So if you took if you just really measured the distance and compared it to what LiDAR tells you. So this is how accurate the LiDAR measurement is. And precision is basically repeatability. So precision tells you that if you take multiple measurements, the LiDAR doesn't move, the object doesn't move, then the consecutive measurements shouldn't be further away from each other than 2, 1, and so on centimeters, depending on the range. What's interesting, because of some optical phenomena, the optimal precision of the LiDAR is within 1 to 10 meters for this specific model, which means that it can be less precise on the first meter of its vicinity as it comes to measurements. Another thing is range resolution, which is basically the resolution of measurement of range. In other words, this is the smallest distance between two objects that the LiDAR can measure. And to illustrate this, it's probably not the best illustration, but that's the best one I was able to come up with. I have this little toy in here, and you can see here that those legs, they are actually, they're not on the same level as the rest of this dinosaur, I guess, right? So this could be as small as 0.1 centimeter, so 1 millimeter, and LiDAR should be able to measure the difference between this depth and this depth. I don't have something that's just 0.1 millimeter. It would be difficult to show in a small demonstration, but I'll show you how this dinosaur works in this LiDAR that I have in here. Other parameters are vertical and horizontal resolution. And to explain those, I'll go to another slide that shows basically a picture from a LiDAR sensor to explain you what those resolutions are. So resolution is basically a number of pixels that you get. And here we have a picture that comes from a LiDAR, but this is just a picture from ambient light. So this is basically LiDAR working as a normal camera, because LiDARs from Ouster can do that, right? And you can see here that this picture, it has a number of pixels vertically and number of pixels horizontally. So how many of those are there? This really depends on the model of the sensor that you have, especially the number of vertical pixels. It really depends on whether you have a model with 32, 64, or 128 channels. Because 32, 64, or 128, this is the number of pixels you can get vertically. Now, horizontally, you can configure your LiDAR to either get 512, 1024, or 2048 points. So this could be up to 2048 points. And then LiDAR repeats this measurement either 10 or 20 times per second. But you have to remember that if you want the LiDAR to spin with 20 hertz, so 20 times per second, then you can get a maximum of 1024 points. And this is, of course, 360 degrees. So this is a all-around measurement. So this is what's here. Vertical resolution is 32, 64, 128. It's just which sensor you have purchased, which model of a sensor you have. And horizontal resolution is the same for all sensors, and you can configure it. Now, the field of view, this is the horizontal and vertical field of view. Horizontal is always 360 degrees because those are 360 degree sensors. They can look 360 degrees all around them. However, vertical resolution is how much up and down can this sensor look. And for this specific sensor, for OS0, it's plus minus 45 degrees. So it's from horizon, 45 degrees up and 45 degrees down. And angular sampling accuracy, this is basically how precise the beam placement is horizontally and vertically. So how repeatable it is that this specific beam is going to look in this many degrees up and this many degrees left or right. Other parameters, false positive rate is 1 in 10,000, which means that 1 in 10,000 samples on average is going to have incorrect data. This could be, for example, because a small particle of dust was just flowing somewhere close to the LiDAR and it was detected rather than an object that's somewhere further away, or just some other optical phenomena happened. Rotation rate, so how many frames per second, how many times you can refresh all of data, is 10 or 20 hertz. And then number of returns is 2. And this is really important because this is a news in Ouster LiDAR. So I wanted to talk a little bit more about this dual returns capability. So Ouster has recently released revision 6 of their LiDARs. All of the models are available in this revision. And this revision has added a special feature, as I said before, called dual returns. This is a feature that basically allows LiDAR to see through objects that are semi-transparent. And I'm talking about objects such as fog or some gases, like you can see on the picture, but this could be also dust, this could be also a fence, or this could be also let's say some leaves, some nature, some pieces of trees or bushes where there are leaves. The way how it works is that if you think of a LiDAR, right, it shoots a laser beam one direction and then it measures what's returning, what has been reflected. But the laser beam is very small when it leaves the LiDAR, but the further it goes, it can get bigger and bigger, all the way up to even single centimeters in diameter. So if you have a laser beam that's slightly bigger, it can hit something where it's partially being reflected back to the LiDAR and partially goes further. Think of such a beam going through a fence. It could hit a part of the fence when some of it is being reflected back, and some of it goes through the fence and will be reflected by something else, let's say a wall of a building that's a few meters behind that fence. In older sensors, we only had one strongest return. So the detector would measure all photons, but return only the data of the highest peak of photons that have been reflected. So probably the element that has been the most that reflected most of the beam. In that case that I just mentioned, probably that would be the building. We would not see the fence at all. With dual returns capability, the detector takes not only the strongest but also the second strongest return. And this way, it can measure also things that are behind or in front that did not give the strongest reflection. And maybe when explaining this in words, it's not very clear. Maybe you can see it a little bit here on the picture when just looking at through the camera, we see a person hidden behind some fog, but LiDAR is able to go through this fog, still see it, still get some points from the fog, but also detect the person that's behind it. But I also have a small movie that I wanted to play. It comes from Ouster. It's a movie that shows a car driving through a pretty dusty road, where you can see a comparison of the real camera and what sensor sees. So in the lower left corner, you can see what camera sees, and here what the sensor sees. And if you look here, the camera can still see the car, but there's more and more dust coming out of its wheels, and it can hardly see it. Oh, right now the camera cannot see the car at all, while the LiDAR can still see some parts of the car, and we can still track it, still see where it is, still recognize it. It's an example of a situation when, on one hand, the LiDAR is better than camera because it can see through fog or some dust that's in the air in this case. And the second thing is that this dual returns capability makes it passable. With all the LiDARs that only had single return, the strongest one, we would still see only the dust and not see the car at all. This is pretty important. There are some projects where it's not important at all, but there are many projects where this is also important because it simply gives you more data. Shortly, I'll be showing you a demonstration of some sample data, and I'll go back to this dual returns capability to show you in practice how much more information can we get thanks to this feature. But before we go to demonstration, I wanted to give you also some more practical information regarding the LiDARs. So imagine you have decided that an Ouster LiDAR is a good solution for your project and you have purchased one of them. So here's what you would get out of the box. And no, I'm not going to make one of those unboxing videos that you can see on YouTube, but I still wanted to show you the key elements of a LiDAR that are shipped with each sensor. So I have moved my camera so that you can see here what I have on my desk, and I'll go through the key elements of the system. So first of all, what you have in here is the LiDAR, right? It's constructed, it's a small sensor, it's not very heavy, it's a few hundred grams. And as you can see here, it has quite a lot of radiators. So it has a top cap, which is a radiator to dissipate heat upwards. And there is also the bottom plate. This can be detached, which is used to mount the sensor, but also to dissipate heat on the bottom. So as you can imagine, the sensor does produce quite a lot of heat, and this is why you need so many radiators to get rid of this heat. There is no fan inside, so it's only cooled by those radiators passively. The LiDAR has only one port, one connector, which is here. The connector is sealed so that it can withstand water and dust. And this connector is used to connect this cable. This is both data and power cable. It has a connector that goes to the LiDAR on one end, and it has an interface box on the other. The interface box has some electronics inside, plus two connectors. One of them is used to connect the power, and it's a standard 24-volt power supply. And the other one is just a classical Ethernet connector. So let me show you now how you can connect everything together. So first of all, I'll take the LiDAR and I'll take the data cable and I'll connect them to each other. Okay. Okay, I think I got it. Now I will connect Ethernet cable on one end to my computer. On the other end to the interface box. And of course, the power supply. Okay, I hope everything is well connected. So now I'll switch also the view from slides to my monitor. Okay, so what you see in here is Ouster Studio. So this is the software that you can download for free from Ouster's website, and this is the software that can be used to configure the sensor and to get data from it and see that data, test that data, and store that data. So what we need to do first is we need to connect to the sensor. I'll press here and I'll wait to see if the sensor has been connected already. I see the sensor has not been found. I'll check if I have connected it correctly. Okay, I think only now I have connected it. I think the cable was not connected correctly. Let's give it a second to boot. Okay, I can see, I think I have heard the scan mechanism to start. Okay, maybe you can hear it now. I'll press rescan again. Yes, and now you can see that the sensor has been found. I can address it either by IP version 4 or IP version 6. Now press connect to sensor. Now I can configure the sensor, so I can configure some communication parameters, and I can also configure how I want the sensor to gather data. So I can choose one of those modes. I think I will choose 1024 times 10. So 1024 measurements per rotation and 10 rotations per second. I'll press configure. So the configuration is sent to the LiDAR right now. It will just take a second. Okay, save configuration parameters and click OK. So right now the Ouster Studio software is establishing connection with the LiDAR, and as you can see, I'm already receiving some data here. So what you can see in here is basically my room. The room you can see behind me. And if we just zoom right here, this is me. I'm moving my head right now. You can see I'm moving my head around my arm around the sensor, and you can see here that this is fairly well visible. I'll move the sensor slightly further away from me so that you can see that if I move my head, you can see my chair. This is this is me in how the sensor can see me. One thing that's interesting is you can see here that there's a little black circle in where we expect the sensor to be. This is because of this dead zone that I mentioned during the when we looked at the parameters. So the sensor cannot see for about 30, maybe 20 something degrees, so centimeters from itself. So this is what we see in here. If you look right now, this is my hand. I think you can see it fairly well. I'll try to move it closer and closer to the LiDAR sensor. By the color, you can see it's getting closer, closer, closer. And now my hand has disappeared. And by the way, also is making so that I'm not visible for a moment by the sensor, because my hand right now, as you can see in the other camera, is very close to the sensor. I'll move it back, and I'm back in the visible zone. If you look at the other elements, this is my room. This is my office room that you can see behind me, so you can see quite well what's in my room. Even things like some paintings or posters that I have on my wall. Oh, sorry. I'll try to move towards them. Here they are. If you look closely, you can see here even the pictures on the wall, which are not very thick. They're roughly maybe 1 centimeter, and they're still very, very, very well visible in this LiDAR image. I'll zoom in back to close to the LiDAR. So maybe like this. Okay. Let me just move this a little closer. Okay, and I'll take my dinosaur as a small example of an object that this LiDAR could detect. Maybe I'll put it here so that you can see that even when I'm moving further, you see that the leg is being detected first, and only later the other elements of the dinosaur. So even small differences in depth can be very well seen and very well detected by this LiDAR. And unfortunately, I have to say that my room is probably not the most exciting and interesting place to be measured by a LiDAR sensor. So I also wanted to show you something else. This is a recording of a drive-through through, I think, some streets in San Francisco where Ouster's headquarters is. This is it's available on Ouster's website, so everyone can go and see sample data readings from various sensors. They did all types of different measurements, and here it will be probably pretty slow because my computer is not able to process a lot of data, but I'll still play it. You can see that on top I have a ambient light view from the LiDAR, so basically like a normal camera. And here, down here, I have an interactive view of the 3D data that's being acquired by the LiDAR in real time. And what I wanted to show you here, maybe I'll switch it for a moment, is you can see that on this street there's quite a lot of trees, and there are also some buildings, and some of those buildings, they also have things like glass walls or glass entrances. So if I'll stop it for a moment, maybe we can find a place like, for example, here. You can see here that there is okay, here there is some door here, and behind that door we can see something else, right? So the LiDAR was able to see through glass and see something behind this door, and similar things in other places. Maybe I'll just play it for a moment longer. Maybe here. Yeah, you can see here that in some places the LiDAR goes behind the glass doors and other elements to see inside. And what I'm going to turn on right now is a special view where we can see data from both the first and the second return. If you remember, the second return was the feature that allowed LiDAR to get also the second strongest returning signal from the laser beam. And here you can see all those green points. Those are the points from the second return. So this is the additional data that we're getting from behind objects, such as trees or glass windows, that give you just more information about the environment. And you can see here that most of those green points are behind trees, like in those cases. But also, for example, here, there's probably a window, and on the left side, we can see that there's a chunk of points from behind the window. So the LiDAR was able to, let's say, sneak in behind the window and get some more information from inside there. So this is why this dual returns feature is so important, and this is why it's useful in some of the projects. So that was a short demonstration, excuse me, the short demonstration I wanted to make. And I wanted to finish today's webinar with just a few example applications of how the Ouster's LiDAR sensors are used in different places around the world. And probably for me and for many people, if you think of a LiDAR sensor, you probably think of autonomous vehicle or autonomous robot. Because this is one of probably the most classical and most common use cases of LiDAR sensors. However, in the last few years, there have been a number of other projects where LiDARs are being successfully used in just different fields of engineering. And so I chose one project at the end about a very specific autonomous vehicle. But before, I wanted to talk about some other projects where LiDARs can be used, and maybe you wouldn't suspect that at the very beginning. In the first place is a project by a company called FlashEye. I think they're from Sweden, if I remember correctly. And the project is monitoring of raw materials processing sites. So think of a place where they store coal or open pit mine, or place where they store sand or stones or other raw materials. The need was to install a distributed measurement system that would have few very different goals, very different tasks. So one task for such a system would be to measure material flows and measure the volumes of materials. So imagine that you have something like you see here on the picture, and you want to know how much sand is here already. So you can use LiDARs to get a map of 3D points on top of this heap of sand, and based on that, measure the amount of sand that's there, just by calculating the volume. However, you can also mount those LiDAR sensors along the conveyor belt that transports the sand, and you can set them to measure the volume of sand that's also lying along the conveyor belt, so that in case of a spillage, in case something is wrong in one place and some sand is falling aside from the conveyor rather than going along it, then such a LiDAR could quickly detect that there's some volume of sand that would not be there normally and raise an alarm. Another thing is that the same LiDAR can not only monitor the raw material, but also machines themselves. It can measure movements of those machines, sometimes even some vibrations. And in this case, it can detect, for example, there's some spillage or there's some strange movement of a machine. And based on that, it can predict that there's some maintenance needed for that machine before everything gets destroyed or damaged in a more serious way. And lastly, the same LiDAR sensors, they can also monitor moving objects, such as people or vehicles, so that they can also in real time try to detect dangerous situations for people and just raise an alarm or maybe turn on a red light or something to make sure that the people's safety is also taken care of. So one system can have multiple purposes and can work in harsh environments, because such places, one, this is outdoors, so the sensor itself, it can It has to work in all types of weather, in all types of temperatures, but also there's a lot of dust, and sometimes the LiDAR will be mounted on the machine itself, and then there's also there's a lot of vibration as well. Lastly, this is a big area, so you need multiple sensors with high ranges that can monitor just very wide area. So it's a project where I would never think of a LiDAR could be useful, and it turns out that this was the best solution for this environment and those challenges. Another project where we see a lot of interest in LiDARs in the last couple of years are smart cities. So many cities all around the world are trying to use smart technologies to make the life of its citizens much better. And here I took an example of Montreal, but there's many other cities that do similar things. Here in Europe, in United States, and in many other places in the world. What those cities do is they're trying to implement so-called smart city solutions. And one of them is to install smart sensors on the most crowded intersections of the city to be able to gather data, monitor, and based on that, either in real time react on the traffic or gather long time data to be able to model human and vehicle flows, and based on that redesign the city, redesign the intersections, try to fix the biggest pain points. Here in this case, the LiDAR sensors have been mounted on a number of key intersections, and their goal is to monitor and record data of movement of pedestrians and vehicles 24/7, 7 days a week for many months. This data is pretty difficult to track because in order to measure and record those flows, you need to, in every point of time, be able to identify or maybe recognize each object separately and measure its path to know where people go from where to where and so on. LiDAR is capable of, LiDAR together with a high-performance PC that can process this data, is capable of gathering a lot of data and monitoring multiple fast-moving objects in the same time. And there's also another feature of LiDAR which might not be very obvious, but it's very important in this type of projects. This is privacy. Because the way how LiDAR works, and you have seen it when you've seen me sitting in my desk through LiDAR's lenses, let's say, you could see I'm a human. You could probably recognize how tall I am and how my body is built, but you didn't see any facial features. So you wouldn't be able to recognize that this was me specifically. So LiDAR by design protects people's privacy by detecting them as humans, but not as specific people, so that you could recognize them and identify them as specific people. This doesn't, so the privacy in this case doesn't need to be ensured in algorithms, which can always be changed, but it's really ensured in hardware. And last but not the least, I didn't want to leave you without an example of an interesting autonomous vehicle, so I took a really big one, and this is mining trucks. Those trucks are used primarily in open pit mining, and this is really a dream application for designing an autonomous vehicle. Because to be fair, it's much easier to design an autonomous mining truck that is moving in a closed space where there's not many humans or people just crossing by, not many other vehicles. The area is pretty predictive, and there's not much unexpected that can happen. So from that point of view, it's a very nice application because it's very simple and safe. But on the other hand, this is an example of an open pit mine in Mongolia, if I remember correctly. And the temperatures they can see there, they go from -40 to plus something, plus a lot. And there's also a lot of dust. There's a lot of humidity in some cases. So the working environment for sensors is really difficult. And again, you need a sensor that will work in any conditions. The sensor that will work if there's some mud on it, a sensor that will work if there's rain, if there's maybe a snowstorm, if it's really cold, or if there's some dust coming from coming from the mine. And again, Lidars were chosen as the best sensors for this project. They were proven to work all the way from -40 degrees Celsius, and they can cover the very complex space around such a vehicle to help it plan path and avoid obstacles. And with that, that was the end of my presentation. I hope you enjoyed it and that you were able to learn something new about LiDAR sensor. If you have an idea for a project where a 3D LiDAR sensor could help you, please feel free to contact us. Here's my direct contact information. You can also find it on our website. You can also connect through us through LinkedIn or however you want. And right now, I will switch to a short survey. It's just 3 questions. If you could answer it, it would really help us make sure that our future webinars are good or even better for the audience. And I'll right now go through the chat window to try to answer any questions that were asked during the webinar. Thank you again for your attention, and I hope to see you on future webinars by Edu for Industry. Goodbye.